let's see how we build the approximator for AND and OR gates, I think. Yeah. So, constructing these approximator circuits. So, we will actually do this by induction in a bottom up fashion. Okay. So, we have our initial circuit C. Okay. So, this is basically as I said. So, we will build a approximator for any circuit, any monotone circuit, and we start with the bottom, that is we start with the input gates and then we will move ahead. So, again, so just to recollect, so what was so I erased the definition. So, what was an approximator circuit? So, we need an OR of at most how many? M many clique indicators, right? And each of these sets have size at most L. Right? So, firstly note that every variable xij is equivalent to the clique indicator Ci comma j, right. So, if because an edge is always a clique, right. So, if there is an edge between ij, that is if xij is true, then ij forms a clique and otherwise not. Now, okay. So, these input variables are already an approximator. Now, suppose we have f okay. Now, suppose f which is equal to an OR of, let us say I going from 1 up to M1 of C x I and G equal to I going from 1 to some M2 again of some C y I are approximators to the input of an AND or gate. Okay, so basically what we are saying is that consider some gate and we have f over here and we have g over here, which are already approximators. Okay, so f is basically an OR of these C xi's and g is OR of C y I going from 1 up to M1 and M2 in f and g respectively. And let us say that this gate is let us call it as, so I have used G over here, let me call this as H. Okay. So, now we will look at both the cases when H is an OR gate and when H is an AND gate. So what is the, so what do we mean by an OR gate over here? Okay, so look at this diagram. So an OR gate will evaluate to 1 if one of these clique indicators are 1, okay, any one of them. Okay. So what is the most natural way of defining the clique indicator for H? So the most natural way would be, so let's call it as F. Okay, so let's say if I define F or G, okay, what do we get? So essentially we get that this is an OR of, okay, one more thing I need to define over here, that these xi's and yi's yeah, they come from a set M. So okay, let me define this thing over here. So let A be the set of all these sets x1 up to xm1, and B be equal to y1 up to ym2. Okay. And one more thing, what do we know about m1 and m2? How large are they? So again, yeah, so we know that by definition of an approximator that it is a clique indicator of at most m clique indicator. Okay. So this is an OR of at most m clique indicators. Okay. So both m1 and m2 are bounded by m. Let me write that here as well. So m1 comma m2 is bounded by m. Okay. Now we come over here. So let's take some x belonging to A union B, and I can look at the clique indicator of x. Okay. Now let's just observe this, that is it actually giving me f or g. So as I said that, well, this function, I mean if H is an OR gate, the function will evaluate to true if one of them is 1, which means that if one of these clique indicators is 1, and that is exactly what I have written here, that look at a clique, I mean look at a set from A union B. If C of x is equal to 1, then this would evaluate to 1. But what is the problem with this definition? A union B potentially might have size greater than m. Okay, so we remember that the definition of approximator says that this x has to come from a collection of sets of size at most m. Okay, so this actually doesn't work. So doesn't work since A union B can be as large as, what is the maximum size? 2m, because each A and B are of size at most m. Okay. So now what we will do is, now we will use the sunflower lemma. Okay, what does the sunflower lemma say? Okay, again I erased it, but anyway. So if we have a collection Z of sets whose size is greater than m, okay, and yeah, whose size is greater than m, where m is that quantity, then it has a sunflower consisting of p petals. Okay. So we apply the, let me just call it SF, we apply the sunflower theorem, and get a sunflower consisting of p petals, and now we replace the sunflower in step 1 with its center. Okay. So, this procedure is also, I mean, this is called as plucking the sunflower. So, it's very simple. It is just so the sunflower. So, because this collection has size greater than m, we are guaranteed about the existence of a sunflower. So, what we do is that we just remove the sunflower and replace it with the center of the sunflower. Okay, and this is, as I said, it's called plucking. Okay. Now, the question is, what does this do to the size of A union B? So, from A union B, I have reduced all these petals, I have removed all these P petals and I have added just one set. So, I have removed P sets and I have added one set. So, it reduces the size of A union B by P minus 1, correct. So, how many times do I need to do this to bring it down to below M? Okay. So, apply the plucking procedure until size of, well, it is not exactly A union B any longer. It is a different set now, until the size of the, let me just call it collection falls below M. Okay. That is at most how many times? So, I had it over here. Yeah, M by P minus 1 plugins. Okay. So, this is easy to see. Again, let me just do this. So, we start with a size at most 2m. So, after I iterations, okay. So, at each iteration we know that we have decreased it by a factor of p minus 1, an additive factor of p minus 1. So, after I iterations we will decrease it by a factor of I p minus 1. Now, if you choose I to be and then I want it to come below m. Okay. Now, if you solve this equation, you will get that if you choose I to be m by p minus 1, then this works. Okay. So, it will affect it, that is why it is called approximator. Okay. So, now we can formally define this. So, we will define the approximator circuit. So, F OR of G is equal to, okay, how do I have it here? It is an OR of I going from 1 to some m prime C, okay, let us say Z I, where m prime is at most m, and Z1 up to Z m prime is obtained from x1 up to x m1, y1 up to y m2 as described above. Okay. So, as we have described above, that if we started with these initial sets and let us say we will end up with the Z1 to Z prime, this is how I define the approximate OR of f and g. So, this is the approximate OR. Yeah, so now similarly we will define the approximate AND as well. So, once again let us see case when H is AND gate. Okay. So, again what is the natural way of doing AND? So, how is AND defined? So, look at this. So, H will output 1 if both f and g are 1. When are both f and g 1? If there is some xi here that because this is an OR of clique indicator. So, there is some clique indicator in f that is 1 and some clique indicator in y in well, some clique indicator in A that is 1 and some clique indicator in B that is 1, right. So, if this is 1, if we have an OR of x in A, y in B such that Cx and Cy are 1. Okay. So, some x and some y. But again, what is the problem with this definition? Huh? How many such tuples will be there, x, y? What is the size of A and B? M1, M2. So, at most M. So, this is, so the number of such tuples x, y will be M square now. Okay, so that is one problem. There is also one more problem. So, this is not an OR of clique indicators, right. So, first problem is that, so these are not clique indicators, and secondly this quantity is at most M square. So, we have to handle both. So, the first part can be handled as follows using the following approximation. So, we will replace Cx and Cy with C x union y. Okay. So, essentially this is kind of saying, this is asking for a lot more. So, here this means that x has to be a clique and y has to be a clique for this to evaluate to 1. Here we are, what we are saying is that the union of x and y have to be a clique. Now, that means that both x and y have to be a clique as well as there have to be edges between these elements of x and y. So, which is actually asking for more, but anyway we are going for approximation. So, we will stick with that. Now, the second problem is, so this at least makes this into a clique indicator. Now, the second problem is we have m square many, it is basically an OR of m square many clique indicators. So, now we again apply the plucking procedure. Okay. So, apply plucking procedure to reduce to an OR of at most m clique indicators. And well, I mean the number of times you have to apply the plucking procedure, you can be a little bit particular here. It will be something like m square divided by m, something like that, but anyway it does not matter. So, you can give a upper bound, that the upper bound on the number of plucking procedures that need to be applied is m square anyway. Each plucking procedure anyway brings it down by 1. Okay. So, at most m square times. Okay. So, now we can define as earlier what is our f and g. So, f and g will be an OR of I going from 1 to some m prime C of it's not exactly okay, let me call it as Z, okay, Zi, where this Z1 up to Zm are obtained as above. Okay. So, we have defined more or less, we have set the framework now. Just one more idea is required, or one more definition is required before we can prove the entire thing. So, this is what is called, and this is quite easy. What is it called? Okay. Let's call it as positive and negative distributions. Okay. So, what we will do is we will define two distributions on n vertex graphs. Okay. So, positive distributions will be those graphs which have a clique of, which are the smallest graphs that have a clique of size k. Okay. And negative distributions will some sense be largest graphs which do not have a clique of size k. So, let y okay, be the following distribution on n vertex graphs. So, what we do is that, so given n and k, of course n and k are inputs. So, pick a set, let us call it as k of size small k, and add edges to every pair of vertices in K. Okay. This is basically the y graphs, and the second one is let n be the following distribution again on n vertex graphs. Okay. So, pick a function f which assigns colors to the vertex in the range 1 up to k minus 1. Okay. So, this is a random function that you are picking, which assigns, so think of this, so think of this as a coloring function. Okay. Let me call it C, it is kind of easy to remember then. So, C is a function which is assigning k minus 1 colors to the vertices in N, and now add edge uv if and only if C of u is not equal to C of v for all u comma v in G. I don't have a name here, so I'll just call it u comma v in the graph. Okay, so simple. So the distributions are very simple to define. It is easy to see that this graph has a k-clique, and if you delete even one edge from this graph, you will not have a k-clique. And here, why does this not have a k-clique?
Suppose there was k-clique, then there would be at least 2 vertices at the same time.
Exactly. So if there was a k-clique by pigeonhole principle, okay, so I have k vertices which forms the clique. By pigeonhole principles, there are 2 vertices in that k-clique which has the same color. Now that is a contradiction, because then I wouldn't have an edge between them if 2 vertices had the same color. So this is the graph which is picked from this distribution doesn't have a k-clique. Okay, so I can write this as follows, that if I use the clique function that we defined at the beginning, so clique k comma n of this yes graph is equal to 1 and clique k comma n of this no graph is 0. Okay, that's it. Okay, so I'll stop here today. So next time we will see, basically now we have all the tools, we know how we approximate the circuit, how we what does it mean to say yeah, I mean what is the clique function. So basically what we will show is that, well, if we have a yes graph, okay, again it cannot be approximated well in some sense, and again if you have a no graph also it cannot be approximated well.